solutions to the system of linear equations. So if we are concerned with the linear equations, then we have several methods. First method we have studied in the linear algebra, and the first method is convert the system of linear equations into the matrix form. Like if you have, for example, you have a 3 cross 3 system. If I write it as a11, a12, yx is the first variable, and is a13 z equals to b1, and again a21x plus a22y plus a23 z equals to b2, and again a31x plus a32y plus a32, okay, and then a33 z equals to b3. So this is the system of linear equations, and we have M is basically, if we generalize this system into the metric system, like if we generalize it, if we have this and to so on, if we have M cross n order, then a m1 x to a m2x to so on, and if we continue this up to a let me modify it, okay, so a13 to so on a1n, and the variable is xn, for example, equals to b1, and if the variable is not a y and z, then I modify it. I replace it as a1n x to the power xn equals to b1, again a23 x3 to so on a1n xn equals to b2 to so on. You can continue it. So a3 m3, basically a m2 x2 and a m3 x3 to so on. You can take it like a mn xn equals to bm. So what m and n shows represents, m is basically number of rows and n is basically number of columns. One more thing is that m, number of rows, also represents a number of equations. And number of columns also shows as number, like x1, x2 to xn. So number of columns also show as number of unknowns. So this is all about the system of linear equations. If you have n journal order linear equation, okay, 3 to x2 and a33 x3 to so on. Okay. So now we move further. Now if I want to convert it into the standardized form, then I can write this coefficient matrix like a11 to amn. If I write it, so I can write it as a, and all the unknowns are from x1 to xn. I can write it as the column vector of unknowns, that is x, and the right hand side of the equation is also a column vector, so that I can write is as ax equals to b. So this is the standard form or the matrix standardized form, and I solve it by using various equations, by using various methods, and that is convert first method is a very simple method, and that is simultaneously you solve the equations simultaneously solve the equations to get the values of the variables. The solution set is of the form x1, x2, x3 to so on xn. Okay, so this is the solution set. First variable, second variable, and all that. So number of columns means unknowns means variables. Okay, so simultaneously solve the equations, and there are various methods like convert it into the echelon form, or also reduced echelon form, and third method is Gauss elimination method, which is our today's topic. And also this echelon form, reduced echelon form, Gauss elimination, Gauss Jordan elimination, which is an extended form of the Gauss elimination. These all involves row operations, or you can also use the column operations if you are convenient. And also there are various methods like so by Cramer's rule you can solve it. So these all and also the purpose is to get the values of the variables x1, x2, x3 to xn. Okay, so now I move towards the next. Okay, so today we will study for that there are the system for having first case 1 is, you know, m is number of equations or number of rows. So case 1 is if m is equal to n. I mean to say that if number of rows equals to number of columns, or number of equations equals to number of solution is unique and system is consistent, right? Okay, so now we move towards the case 2, and case 2 is that if m is less than n, you know that the number of equations are less here and the number of unknowns are more here. So it is difficult to sort out the number. There are basically extra number of variables involved in it. System is consistent, but you can write the extra variables. You can write the basic variables in terms of the free variables, extra variables. So your system is consistent, but you get infinitely many solutions. Okay, so this is all about the consistency of the system. And case number 3 is if m is greater than n, that means that number of equations are greater and number of unknowns are less. And you leads to contradiction, like if you have some 0 equals to some non-zero constant, if you reach to that type of conclusion, that means like if you reach to 0 equals to 7, so that means it is a contradiction. If this case arises, then your system is inconsistent. Okay, so these are basic 3 cases which it can arise into while following any method. Okay, so now we come towards our basic method, our today's topic, and that today's topic is basically the history of the previous basic matrix structure, how to construct the equations into the matrix. So today's topic is Gaussian elimination or Gauss elimination method. It can also be known as Naive-Gauss elimination method. So this method involves two steps. Step number one is reduce, or I would say convert the matrix or given system into, or matrix into, upper triangular form. So if you convert upper triangular form, it can be possible that you select the pivot positions. Like in the first row, your pivot position is A11, so you have to divide first equation with A11. That is the pivot position, right? Okay, and in next is divide the second equation with the next pivot position of the second row by A22. That is the next pivot position, and so on. Your last equation will be divide the mth equation, if you have the journal equation. If you have journal equation like if divide mth equation with its pivot element AMN to get the matrix into upper triangular form U. Okay, now what you will do, you will convert this equation, you will write this matrix, basically the given matrix. I would say it is a given matrix. Okay, so to convert the given matrix into upper triangular form, and I told you the procedure, that divide the first equation with the first pivot position, second equation with the second pivot position, and so on, mth equation with the AMN pivot position to get the upper triangular form. Now convert this matrix, convert the matrix into the equations, okay, as given in the equation. Okay, so step number two is a very basic. So that is basically, we say it as back substitution. Back substitution means the last variable can be derived by xn, can be derived by this. So this is a coefficient, this is the constant, xn is found by or determined by this. And again the second last equation will be, so if you suppose the 3x3 system, then we can say that, for example, A33 into x3 is equal to b3. So x3 is derived like this, it is a constant here. And again, back substitution means you start with the last equation and you reach up to the next equation. So the second last equation will be A22 into x2 plus A23 into x3. Now x3 is found out by this equation. So this is equation number 1, and it is equal to b2. So replace the value here and you can get, and rearrange it to get the x2, right? And the last step is, that is equation number 2. The last step is A11 x1 plus A12 x2 plus A13 x3 equals to b1. So b1 is also a constant. Replace the value of x2 here, replace the value of x3 here to get the value of x1. So this is equation number 3. Now your solution set will be x1, x2, x3 will be one value, second value, and third value. So this is the basic procedure of the Gauss elimination method. The first step is also known as the echelon form, but it is also known as the upper triangular form. So it depends. Use Gauss elimination method. Basically it is a forward upper triangular form, and the step number 2 is backward substitution. So naive Gauss elimination method to solve the system. Okay, so first equation is x plus 2y plus z equals to 8, and the second equation is 2x plus 3y plus 4z equals to 20, and the third equation is 4x plus 3y plus 2z equals to 16. Now what you have to do in Gauss elimination, it is all about your row operations. So I have told you, name these equations or convert it into the matrix. So this is first equation, this is second equation, and this one is third equation. So if I convert it into the matrix Ax equals to b, then the coefficient matrix will be, first variable has the coefficient 1, then 2, then 1, then 2, 3, 4, 4, 3, 2. Okay, and x is x, y, z. So this is basically the simplest form of the matrix system. 8, 20, 16. Okay, so now I convert this matrix into the augmented system. Augmented matrix is basically A, B. Now you can write it as, because in every row operation the constant b affects in that row. So 1, 2, 1, 8, 2, 3, 4, 20, 4, 3, 2, 16. Okay, now we solve equation number 1. So the pivot position here is 1. So if we don't need to divide with a11 coefficient because it is already 1. So what we will do, we will reduce this matrix into the upper triangular. Upper triangular means that only your diagonal and the upper entries are non-zero, and rest of the entries should be equal to 0. So to make 2 0 and 4 0, you have to do the row operations. Okay, so first is you have to convert this 2 into 0. Then you need the row operation, that is R2 minus to make R2 first element in that column, first column, second row, element 0, you have to multiply it to R1. So it affects, whatever affects in, you have to write it first. So the change is in R2. So write R1 as it is. Okay, R2 means R2 minus R1. 2 minus 2 into 1, that makes it 0. And 3 minus 2 into 2. So 3 minus 4 is minus 1. So you can write it like minus 1. And then 4 minus 2 into 1. So 4 minus 2 is 2. Again, this is the change in the constant vector, and that is 20 minus 2 into 8. So 20 minus 16 is 4. Okay, so I remove this. Now within this step you can also calculate this row operation, next row operation in the next step, but I am writing it here, and you have to convert this for equals to 0. So for that you should apply the row operation R3, you have to change the element. So R3 minus 4 into R1. Okay, so you have to multiply it, then it becomes 0. 4 minus 4 into 1 equals to 0. And 3 minus 4 into 2. So 3 minus 8 is minus 5. And 2 minus 4 into 1. So 2 minus 4 is minus 2. And 16 minus 4 into 8. 16 minus, that makes it 16 minus 8 into 4 is 32. So that makes it minus 16. Okay, so this is the change. Now for upper triangular, you have to make this entry equals to 0. Okay, so make it 0. Now in the next step, what we will do one row operation, and that row operation is, you can see that if I have to change the R3 and I have to make this minus 5 equals to 0. So R3 plus 5 into plus, or I think what's the mistake here? 3 minus 2 into the minus 1. Okay, so okay, R3 minus 5 R2. So minus minus becomes positive. Okay, so there is no change in first row. So 1 to 1, 8. There is no change in R2. It remains as it is. And the next step is 0, 5 minus 5 into minus 1, minus 5, minus 5 into minus 1, minus 5 plus 5 equals to 0. So you can write it like this, 0, and 2 minus 5, minus 2 basically, minus 5 into 2. So minus 2 minus 10 makes it minus 12. Okay, and third one is your constant vector, and your constant vector is minus 16 minus 5 into 4, minus 16 minus 20. That makes it minus 36. Okay, now your matrix is converted into, that is step number 1 is done. Okay, step number 1 is completely done. So your matrix is converted into upper triangular form. Now you can write this into the equation, and equation is 1 into x plus 2 into y plus 4 into z equals to 8. And we start with the back substitution in the next step. Okay, and x has the coefficient 0, then minus y plus 2z equals to 4, and the third one is minus 12 equals to minus 30, 12z equals to minus 36. Now we solve this by using the back substitution, like this and like this. Okay, now we start with this equation number 3. This is equation number 2 here, or equation number 1 here. So we start with the equation number 3. If we solve this, z equals to minus 36 minus 12. That makes it 3. So z is 3. Now I put the value in equation 2, that makes it minus y plus 2 into 3 equals to 4, minus y plus 6 equals to 4, minus y, if I shift into the other side, it becomes 4 minus 6, and then minus y equals to minus 2, so y equals to 2. Now I put the value of this z equals to 3 and y equals to 2 in equation 1. So what it becomes, x3, so x plus 7 equals to 8 and x equals to 1. So this is the solution set, and that solution set is by Gaussian elimination procedure. So So this is the back substitution process. This all is step number 2. Okay, so our solution set is 1, 2, 3. So this is a basic Gaussian elimination method, and in the next slide, or in the next video, we will do its modified form, that is Gauss-Jordan. I hope that you understand. It's a very simple method. All you need is the basic row operations and nothing else.